Hello, friends. Jim here. Welcome to Science Talk. Well, look at this headline here that appeared in the online publication EOS. Arctic warming triggers abrupt ecosystem shift in North America's deepest lake. Great Slave Lake's huge cold water mass shielded it from impact of the rapidly warming climate. Until now. What is going on? Okay, so here's a image of the Great Slave Lake in Canada's Northwest Territories. It's North America's deepest lake. And we can see this is the Slave River coming out. There's the Hay River this way. And here's the lake itself. It's I think it's near the town of Yellowknife. The lake looks like they say a giant goose. Well, I guess that must be the neck then. Okay, they say so. It's found in Canada's Northwest Territories. It's the area the size of Belgium. It reaches depths of up to 614 meters. It's the 10th largest freshwater lake in the world, North America's deepest freshwater lake. Its huge mass of cold water helps shield Great Slave Lake from the climate impacts that have upended the ecosystem of shallower lakes in high northern latitudes. That has changed now, according to a study in the Proceedings of the Royal Society B. Spurred by accelerating Arctic warming, right? It's now 4, maybe 5 times faster than the rest of the planet. The microscopic producers, the phytoplankton that form the basis of the food web, have made a radical regime shift since the turn of this century. The single-cell organisms, the diatoms, right? Diatoms are a cold water phytoplankton. They tend to create shells or tests that are made of silica. And when they die, they settle down, they get buried, they get preserved in lake sediment record. And when you do a sediment core, you can analyze this. This is standard technique done marine systems, freshwater systems, all over the place. You pull up a sediment core sample, and you analyze it, and you can actually identify the organisms that live there. That would include phytoplankton, even zooplankton, and other, say, invertebrates, for example. By analyzing the sediment, scientists found that these diatoms that have been the dominant producers in Great Slave Lake have now been supplanted by smaller other species. This upheaval in the system's primary energy source could affect the lake's productivity and carbon dynamics, alter its food web, disturb a significant food and cultural resource for nearby First Nations and Métis communities. In recent history, which we can link to climate warming and less ice cover, it's a profound change, said John Small, a paleolimnologist at Queen's University in Kingston, Ontario, Canada. A limnologist is the freshwater lakes equivalent to an oceanographer. Limnologist studies freshwater systems, could be lakes, rivers, what have you. If it's lakes, it's the lotic branch. If it's rivers, it's the lentic branch. But basically, these are the freshwater scientists. So they do a lot of what oceanographers do. They may look at the physics, they'll look at the biology, measure productivity, look at the chemical species, look at the geology, and so forth and so on. This gentleman here was a co-author on that study. Although the consequences of the regime shift are not yet known, maybe it's too soon to tell or to see the effects, Small said the impacts are almost certain to cascade throughout the ecosystem. Well, if you're changing the producers, and if they're smaller, that's going to impact, say, secondary productivity, zooplankton growth, which, and they're impacted, then that impacts the larval fish that feed upon them, which impacts the bigger fish that feed on the larval fish, and so on and so forth, up to, say, a heron or a kingfisher that goes and grabs fish from the lake. So what Small did was, and his colleagues, they compared lake bottom cores extracted in 2014 and the mid 1990s, about 20-year time difference. The two sets of cores provided sediment records stretching back about 200 years. That's pretty decent. From which researchers analyzed diatom remains for changes in species abundance that signal ecosystem transition. Sediments show that for much of the past century, the lake's ecosystem was dominated by Olacosera icelandica, which is a heavy 20 micrometer diameter diatom shaped like a tin can. And that is what this photo is of. But beginning in the mid 1990s, a heterotrophic array of small buoyant plankton, about a tenth that size, so 2 microns, began to move in. Heterotrophic means just a array of a whole bunch of different characters, different species. This shift started ramping up around the turn of the century, and by the mid 2010s, they had basically taken over. So let's look at this photograph. We can see the scale here. This bar of this length here is represents 5 micrometers, and you can see that you apply this, yeah, it's about 25 microns in length here, whereas this is only 2 microns, and that looks like maybe a radius of 3 microns, so maybe a diameter of 6 microns, 4 to 6 microns, considerably smaller. Right? So this is the Olocosera islandica on the left side here, and then we have Discotella species on the right side here. And that's an example of one of the smaller phytoplanktons moving in. So lake scientists are surprised and concerned by this radical transition, which is unprecedented in the sediment record because of the rapidity in which it occurred. Although a warming climate has been triggering rapid shifts in smaller and medium-sized northern lakes since the mid-1990s, the findings showed that very large bodies like Great Slave Lake, which had until recently been protected by their extensive ice cover and thermal inertia, are no longer able to stave off the changes. The nature and magnitude of these effects is startling, said Warwick Vincent, an ecologist specializing in Arctic lakes at Laval University in Quebec, not involved in the study. We expected North America's deepest lake to have a large buffer capacity against global climate change. This now seems to have been exceeded. So rising temperatures, declining ice cover, slowing wind. These are probable factors that have led to this regime shift. Great Slave Lake's abrupt transformation corresponds to accelerating Arctic climate change, said the study's lead author, Queen's University paleolimnologist Kathleen Rulin. The region is now warming several times faster than the global average. Right? We talked about Arctic amplification many times on this channel. I've done studies, I've shared studies with you where the Arctic is warming in some places 5 times faster than the rest of the planet. And what happens in the Arctic does not stay there. It spreads. Since 2010, air temperature in the Arctic have climbed by 1°C. Okay, we're talking about the whole planet of like 1.3, 1.5, right? Over how many decades? You know, a century plus at least, and in 1+ decade, bang, the Arctic has warmed up 1°C. Think about that. Lake ice cover has also declined significantly. Wind speeds have slowed. Now, this is important. The wind speeds have slowed. That means mixing is reduced. And if mixing is reduced, you're not going to stir up the water column. You're not going to get the overturn to pull in nutrients up into the photic zone. So Rulin says the lake is growing calmer, which is bad news for the large phytoplankton like A. islandica that require turbulence to stay afloat and excuse me, be able to have light activate the electron transport chain system for photosynthetic processes to take place. Without the turbulence and the mixing, they sink out of the water column. They sink out of the photic zone. But if you're a smaller phytoplankton that has a higher buoyancy, that's fine for you guys, right? They're going to be able to hang out. But a regime shift is an early warning sign that things are really changing. Further research monitoring are needed to determine the broader implications. One obvious question is, how will this impact primary production or the creation of organic matter, right, from inorganic carbon compounds, right? How does this impact primary production? How does this impact the food web, the food chain? Of course, therefore, how does this impact secondary productivity? Between 2003 and 2018, primary production in Great Slave Lake rose 27%, according to a remote sensing study in the journal Water. But the smaller algae now driving the food web could provide less nutrition for the organisms that eat them, which means it affects the food supply for fish and other aquatic life, meaning that they're providing less nutrition. Secondary, tertiary productivity, despite primary productivity increasing, secondary and tertiary productivity will decrease. In addition, the amount of carbon the new regime sequesters through primary production could rise or fall. Researchers are now turning their attention to the Northwest Territory's Great Bear Lake, which is further north. It's colder and even larger than Great Slave Lake, though not as deep. Preliminary data on this lake, Great Bear Lake, the 8th largest in the world, suggests a similar upheaval is underway there as well. We think of the Arctic as the miners' canaries of the planet, and the lakes are recording it. And within the lake, the canaries are probably the algae. So now I have discussed with you the fact that in the Bering Sea, has been documented a regime shift in the phytoplankton there, from the diatoms have been replaced by coccolithophorids. Coccoliths prefer warmer water temperatures. That is impacting productivity there. It's impacting the cod ultimately. Cod, an important fish in the Gulf of Alaska and in the Bering Sea and so forth. In fact, it's actually both regions. It's the Bering Sea and the Gulf of Alaska. The diatoms are being replaced by coccoliths. So that's impacting the zooplankton productivity, which impacts the organisms that feed on the zoops, which we call zooplankton zoops for short, and all the way up to cod. Well, if you have zooplankton productivity impacted, which then has a ripple effect up through the rest of the food web, you can, be pretty confident that cod will be adversely affected, and we're seeing that. So if we're seeing this change from a diatom to a much smaller non-diatom, that is going to have major implications for the food web, for productivity. And as stated here earlier, right, they said that primary productivity rose 27%, but it was less nutritious for the organisms that come after. So that means secondary, tertiary productivity will decrease. And the way they just look at, you send satellites over, you look at you have color codes, what have you, and you can actually see the blooms, and you estimate productivity from the blooms. So overall, this is very troubling. Very troubling. We'll have to see what happens down the line. I don't think it will be good. Until next time, thank you for your time.